Alright guys, in this section we're going to be discussing vectors in the plane. And vectors are very useful tools for modeling and solving real-life problems. There are quantities such as force and velocity that involve both a magnitude and direction and cannot be completely represented or characterized by a single real number. In those cases, to represent such quantities, we can use a directed line segment to get an idea, more of a visual representation of these quantities. So let's say we have a directed line here, somewhere on the plane. So let's pretend this platform here, or this board, or your piece of paper is just the plane here, a two-dimensional plane, and we're going to have our directed line come from starting at P, point P, going all the way to point Q. So this point P we're going to call the initial point, and Q is going to be our terminal point. Now, so this is very important here because this is not just a line segment, but it's a directed line segment, so it matters where we're starting and where we're ending. So we'll represent this directed line as the line segment PQ. We put a little arrow on top of it to indicate the direction too. So PQ would be different than QP, right? It's the order there. So that indicates our direction, that we're coming from P, or that the line starting at P going all the way to Q. Now, so this vector representation is going to have a magnitude, and the magnitude is nothing but the length of this ray right here, this line segment. And we're going to represent magnitude with double bars, horizontal bars here. It's kind of like looks like an absolute value, and it's going to be calculated basically using our distance formula. So if you recall from your algebra course, if you have 2 points in the plane and you like to find the distance between them, we have a nice formula that says, if let's say we label these points to be for Q1, Q2, and P is P1, P2, some arbitrary points on the plane, the distance formula says that the distance or the length of this line segment, PQ, is going to be the difference on the x coordinates square plus the difference of the y coordinates square. So in other words, Q1 minus P1, all of it is square, plus Q2 minus P2, all of it is square. And of course, the square root of all that. So that's distance formula. Well, for us, that's what's going to represent magnitude of a vector. So the magnitude of PQ is going to be basically the distance or the length of that ray. Now, our convention here is going to be to label vectors with, usually we use the lowercase v, u, w, and in your book or most textbooks would represent those with bold lowercase letters. Right? Sometimes I would put a line or an arrow on top of it just to distinguish it from any other variable or any other letter, so do you know we're talking about vectors here. Now note that two vectors here are going to be equivalent if they have the same magnitude and the same direction. So remember, the whole point of introducing vectors here is that there are going to be quantities that cannot be represented with a single number. So they're going to need a vector, they're going to need a magnitude and a direction. If we have two vectors that have the same magnitude and direction, then they're really, or two directed lines that have the same magnitude and direction, they're really the same vector. Because I can move this vector around anywhere on the plane. If I don't change the magnitude or the direction, I'm still talking about the same vector. So here's an example where we have two vectors, and you see the picture on the right there, u and v, and we want to show that they're at equivalent, right? So the way to prove or show that the magnitudes of both are equal, so we'll compute the magnitude of u, which is pq. Notice how p is the origin, 0, 0, q is 3, 1. So I'm just going to use my distance formula here, my definition of magnitude, to find the magnitude of vector u, which is the directed line PQ. Okay, after putting all those coordinates in there into my formula, I get that the magnitude of u is square root of 10. Okay, in the same way, I'm going to find the magnitude of v, and that is the directed line RS. And we have the coordinates of the initial point and the terminal point, and we apply our formula, and we're going to get that the magnitude of v is also square root of 10, proving that they in fact have the same magnitude. Now we need to find now that we need to show also that they both have the same direction as well. And to show the direction, or to determine direction of a vector, there's different ways that we can approach and compare directions. But basically, one easy way that you're familiar with is finding the slope of that line, right? So since we already have 2 points on both of these lines, on both of these vectors, then we're going to use our rise over run, or difference in the y over the difference in the x, to find the slope of both of these. So the slope of the line in the direction of PQ is going to be 1/3. The same way, if we find the slope of the line in the direction of RS, we'll find that that's also equal to 1/3. So proving again that they both have the same direction, because if they have the same slope, they're going in the same direction, they're never going to intercept. They're parallel lines in that sense, so they have the same direction. Then showing now with this that both vectors u and v are equivalent. Since they have the same magnitude in the same direction, u and v are equivalent. And now, so to pretend like you could move v and put it on top of u, or u on top of v, it would be the exact same vector. Now, since we have an infinite amount of ways that we can move a vector around in the plane and place an infinite amount of positions where you could place a vector in the plane or a directed line, and if you don't change the direction and the magnitude, we're talking about the same vector, we're going to introduce a standard position that's going to help us define a unique representation for each vector. So instead of having an infinite amount of ways of representing the same vector, we're going to look at one position here that will give us a unique representation we're going to call the component form of a vector. So if we place our vector so that the initial point starts at the origin, 0, 0, so your p is 0, 0, and your q would be wherever that terminal point happens to be. So I'm going to label my terminal point with coordinates v1, v2, okay? And our component form is going to be determined by subtract the x coordinates, the y coordinates. So if you do that in standard position, notice how you're going to get that q1 minus p1, given p and q here, is going to be equal to the v1, which is the coordinate of the terminal point in the standard position. And the same way for v2 is going to be equal to q2 minus p2. This way we present a unique representation of each vector. This way, no matter where we move this vector in the plane, we're always going to get this difference. It's always going to be v1. That difference is going to be v1, v2. Now you can see that right away because those quantities v1, v2 would match that terminal point if the directed line is in standard position. Now the magnitude becomes now, instead of what we had before, the square root of that difference of the x squared plus the difference of the y squared, becomes just the square root of v1 squared plus v2 squared. We use what I like to call them as triangular brackets here to represent a vector now. We have this component form, two components here, v1 and v2. Now keep in mind, this is not an order pair, right? It's not a parenthesis. So let's look at an example here. Find the component form and magnitude of the vector v that has initial point -2, 3 and terminal point -7, 9. Again, calculating the difference there, the x coordinates and the y coordinates, and putting that in triangular brackets, we get that vector v is going to be equal to -7 minus -2, 9 minus 3. Is that equal to and that's equal to -5, 6 in triangular brackets. Now finding the magnitude, it's a lot easier if we just look at the component form of the vector here that we just found. Instead of doing the difference of the x and the y's again, we just look at the components there, -5 squared plus 6 squared, and we're going to take the square root of all that, and that's going to be equal to the square root of 61. There we have it. Now that we've defined what vectors are, we are going to have some vector operations that we're going to be able to apply to vectors. So we're going to see vector addition and scalar multiplication, and given u and v vectors, and we have their component form right there, and k be a scalar, and when we say scalar we're referring to a real number. Now if we have u and v, and I copied them here on the right again, if you literally move that second vector, you're going to add u and v, geometrically, graphically, what we're doing is if you move the second vector so that the initial point of the second vector, which is v for us, matches with the terminal point of the first vector, in this case u, then the directed line from the initial point of u to the terminal point of v is the sum of the two vectors. In other words, u plus v. So notice how if you add two vectors, you get another vector back. And this is what we call also the resultant vector. When you hear the resultant vector, we're talking about the sum of two or more vectors. In this case, we're doing the example with two vectors, u and v. Okay, so that's what the sum represents. It's a very straightforward process here for addition. You just add the components. If you have vector u and vector v, you just get another vector where each component is the sum of the components of the other two vectors, u1 plus v1, comma u2 plus v2. The important thing to notice here is that we get a vector back. In the same way for scalar multiplication, when you're doing scalar multiplication, is just like the name itself suggests here, is you're really scaling, right, the vectors. Notice how giving a u here, if I multiply u times some scalar, some real number 2, all I'm doing is I'm doubling the length here, the magnitude of that array. So it becomes double. If I multiply by 1/2, I cut that in half. I'm scaling it so that it's half the length of what u was, right? So that's really all you're doing. The math, it looks like you're distributing that k, so it just distributes to every component there, k u1, comma k u2. All right, here we have some examples to practice these operations. And so given u equal to 1,4 and v equal to 3,2, find each vector here. And notice how all of these are going to give us a vector back. So we should have a component form at the end, right? So adding the components here, we're just doing u plus v. We get our first component, we get 1 plus 3, comma 4 plus 2, and the second one there, so the vector is 4, 6. All right, for the next one, we're calculating u minus v. We're going to have 1,4 minus 3,2. Now, something that I forgot to mention here on the scalar multiplication, that if you multiply, k is any real number, so if you multiply the vector by a negative number, and let's say just -1, the negative is going to change the direction of the vector, and exactly the opposite direction. So it's like a 180-degree turn. And of course, if you have any other negative number, it also scales it to that, but the negative changes the direction in exactly the opposite direction of the original vector. And the math is the same, it's pretty straightforward. You just subtract, and we're going to get 1 minus 3, 4 minus 2, that's -2, 2. For our third example, we have a little bit of both, a scalar multiplication with one of them being negative, and ultimately adding both as well. And we're going to get 2 minus 9, 8 minus 6, giving us a final vector of -7, 2. There you have it. All right, so here are some properties of vector addition and scalar multiplication, and these are analogous to the properties for real numbers, right? So vector addition and scalar multiplication are well defined, so most of these properties from the real numbers also apply here for vectors. You see the commutative property, the distributive property. So just make sure you understand which ones are vectors, which are represented in bold letters, and which ones are scalar. Here are some examples how you use some of these rules. I wanted to show how to use that last rule there, number 9, where you have a scalar multiplication. So C is a scalar, you're multiplying it times the vector V, and you want to find the magnitude of that. But the rule says there that you can pull out the absolute value of that scalar, C, outside, and you just find the magnitude of the vector itself. So that's what we're doing. I'm just showing you how you can apply the rules here. Pull out the 3 out, and notice it has an absolute value. So because magnitude, remember from the definition, is length of that ray, so we're not going to have a negative magnitude. That wouldn't make any sense since we're talking about length. So that scalar has to be in an absolute value, like on this second one here, right? Even though we have negative 2v, the rule says you take negative 2 in an absolute value, which is ultimately going to be equal to 2 times the magnitude of v. And we already know how to calculate magnitudes given our component form of the vector. So that's a pretty straightforward process there. Okay, in the same way, you can apply all the other rules. Like I said, most of those rules should look familiar to you just from rules of the properties of real numbers. So there we have it. All right, so another definition that we need to understand is unit vectors. And unit vectors are just going to be vectors with magnitude of 1. So remember this word unit, we've seen it in unit circle, and you might have seen it in another context in math, but typically the word unit refers to number 1. So in this case, unit vectors are going to be vectors with magnitude of 1, and we've seen scalar multiplication, so we're going to use that with our definition of unit vectors to determine always a unit vector in the direction of another given vector. So if you're giving a vector v and you want to find a unit vector in the same direction of v, then all you're going to do is divide that vector by its own magnitude, right, as you see there. So all you're doing is really multiplying the vector v by the reciprocal of its magnitude. So 1 over the magnitude of v. Now the magnitude of any vector is just a scalar. So 1 over that is still a scalar, a real number. So you're really just using scalar multiplication to get another vector, right? Where the scalar is 1 over the magnitude of v. You're multiplying that times the vector v. That's going to give you a vector u that has magnitude 1. So this is the process of finding a unit vector in the direction of another given vector. Okay, so let's look at an example here. We're going to find a unit vector u in the direction of v, and v is 6, -1, and verify that the magnitude of u is in fact 1. Okay, so using the form from above here, we're going to take our vector v, 6, -1, and just divide that by its own magnitude. Now remember how the vector is in triangular brackets and the denominator is a scalar. We're just calculating what the magnitude is there. We still have the vector 6, -1. We're going to divide that by the square root of 37. Okay, so that's equivalent of saying 1 over square root of 37 times the vector v, which is 6, -1. We've seen how to scalar multiply, and we just distribute that 1 over square root of 37 to each component, and we get the vector 6 over square root of 37, -1 over the square root of 37. And that's your vector u. That's supposed to be a unit vector. So let's go ahead and verify that u is in fact a unit vector by checking its magnitude. Magnitude of u is equal to the square root of the first component square, 6 over the square root of 37 square, plus -1 over the square root of 37 square. So the second component square. All of that is under the square root. And once we evaluate the squares, add them up, we're going to get the square root of 36 over 37 plus 1 over 37, which is square root of 37 over 37. Square root of 1 is just 1, so that checks out, right? u is in fact a unit vector since it has a magnitude 1. Okay, now that we know what unit vectors are, we need to define what standard unit vectors are. And the standard unit vectors are going to be just the unit vectors that are right along the axis here, the x-axis and the y-axis. So the one that is in the direction of the x-axis is going to be called I, and the one that goes along the y-axis is called j, right? And you can see the representation in component form. I is 1, 0, j is 0, 1. And what I have here is that given any vector v, or an arbitrary vector v, v1, v2, I can write any vector as a linear combination of the standard unit vectors. In other words, it's a linear combination of i's and j's, as you see here in this proof, right? Using our vector addition and scalar multiplication, I can just rewrite v as v1i plus v2j. And this v1 becomes our horizontal component. This v2 is our vertical component, right? Because they're the coefficients of the I and j respectively, okay? So this is what we call a linear combination of i's and j's, or standard unit vectors. So let's look at an example here and see how we can represent this as a linear combination of the standard unit vectors. We have a vector u whose initial point is -2, 6, and terminal point is -8, 3. We want to write u as a linear combination of the standard unit vectors I and j. So we already know how to write a component form given the initial and terminal point. We know how to write a component form of a vector, and so we'll do that first. And we always remember to start with the terminal coordinate, right? Whether it's the x or the y. First the x, -8 minus -2, 3 minus 6. Always start with the terminal, because otherwise if you switch those, you start with the initial, you're going to be doing a different vector. You're going to be switching the initial and terminal points. You don't want to do that. So once we get our component form, -6, -3, what we have from above, very simple, very straightforward. I can also represent this vector as a linear combination of I and j's by just get the components -6i minus 3j. And there you have it. Now here we have another example where we're given just two vectors as the linear combinations of i's and j's, and we're asked to find 5u minus 2v. Now this is just an example of using our vector operations, vector addition and scalar multiplication, but they're giving you the vectors in with the other representation as a linear combination of i's and j's. Just to show you that it's the same thing. It's just another way of representing the same vectors. So 5u minus 2v would be equal to 5 times I minus 2j, which is vector u, minus 2 times -3i plus 2j, which is vector v. Okay, you would treat this as a normal distribution here. Now notice how when we write this as a vector as a linear combination of i's and j's, there's no brackets, there's no commas. It's literally a sum, guys. So distributing the 5, distributing the -2, we get some terms they have i's, some terms they have j's. We combine like terms like you would normally do with any variable, and we get 11i minus 14j is our final vector. Remember, we're adding vectors here, so our answer is going to be a vector, right? Just like we did previously on the example with vector addition. Now, just to show you that it's the same thing as if we had done this in component form, we can write u and v in component form, right? Instead of having the i's and j's, I just have in triangular brackets, I have 1, -2, and for v, I have -3, 2. And I can do the same operation just in component form, right? You already know how to scalar multiply and how to add two vectors. So we do exactly that. And notice how we get exactly the same thing, just in different notation. 11, -14, which is equivalent to 11i minus 14j. All right. And one last thing here, guys, we want to go over in this section is direction angles. Now, direction angles are going to be basically the angle formed with the positive x-axis and the vector itself, the vector being in standard position. So remember, standard position, we start at the origin, and wherever the vector may be, whichever quadrant may be in, the direction angle is going to be the angle starting in the positive x-axis. In this graph here, theta is the direction angle of the vector u. Now notice how if I put this in a unit circle, or in other words, if my vector u is a unit vector, then x comma y, that coordinate x comma y in the plane, becomes cosine of theta comma sine of theta from our unit circle. We know this. We've done this since the beginning. Now, writing as a linear combination of i's and j's, I can also say that vector u is cosine of theta I plus sine of theta j. Because remember, this cosine theta, sine theta are just the components of the vector, right? v1 comma v2. So I can also write it using the other representation with the standard unit vectors, where this theta is now what we call the direction angle of vector u. Now, what happens when the vector is not a unit vector, right? So let's assume v is just a vector equal to ai plus bj, and it makes an angle theta with the positive x-axis. Then it has the same direction as u. You can write now. Remember how we've seen how to scale any vector so that it has magnitude 1. In other words, come up with a unit vector that has the same direction of u. I can take that vector v, divide it by its own magnitude. Again, I get a unit vector, and let's say that's u here, and use the representation that I have here with above with my direction angle. Since I already have a representation with cosine and sine of the direction angle for a unit vector, then I can think of v as a vector that is equal to the magnitude of itself, of v in this case, times u, this unit vector u in the direction of v, right? And you can just see that from our equation here on the left, where v over magnitude of v is equal to u. So solving for v, I get that. And since u is, again, cosine theta comma sine theta, I can replace that for u, and v, magnitude of v is just a scalar, so I can distribute that, write it as a linear combination of the i's and j's, and have this final representation of vector v, right? Well, you may ask, well, how do we find the direction angle if we have all the other information, okay? If you're asked to find the direction angle, or in this case theta, we're going to use just our basic trigonometry here, and we know that tangent of theta, of tangent of any angle, is equal to sine of the angle divided by the cosine of the same angle. And since this vector v is equal to ai plus bj for some arbitrary a and some arbitrary b, then this magnitude of v times cosine of theta is really just that a, that coefficient there, a, and that multiple a. And the magnitude of v sine of theta is really that multiple b there in front of the j. So if I just do a little bit of algebra here and multiply my sine and cosine by magnitude of v, then I just get b over a. And there you have it. Tangent of theta is equal to b over a. So if you want to find theta, you're just going to have to use your trig or your inverse tangent to find the angle theta, the direction angle here. So let's look at some examples here. Where we want to find the direction angle of each vector here, and the vector on the first one is negative 6i plus 6j. A is negative 6, b is 6. Using our setup here, tangent of theta, or tangent of the direction angle, is equal to 6 over negative 6. That's equal to negative 1. And then you ask yourself, well, when is tangent negative 1? If you think about your trig, unit circle, first of all, it's negative in the second and fourth quadrant. But if you were to graph this vector here in standard position, the vector is actually in the second quadrant. So we need to think about that. And also, this negative 1 actually happens to be nice. We can figure that out from using our unit circle. So tangent is negative 1 at 3/4 and 7/4. But since the vector is in the second quadrant, 3/4 is the one, is our direction angle. Now in degrees, that's 135 degrees. So make sure you know where the vector is, what quadrant the vector is in, to be able to get the right direction angle. In the same way, for the next example, we have the tangent of theta is equal to b over a. B is -4, a is -7. That's going to be equal to 4/7 because the negatives cancel out. Now this one here, we don't know from the inner circle, but just think about where v is here. And even though tangent is positive on the first and third quadrant, the vector is on the third quadrant, so that's the angle that we're looking for. Okay, so and we're gonna have to use our tangent to find the value here because this 4/7 is not a known value from the inner circle. So if we set it up as with our tangent is going to give you that first quadrant angle. So I'm going to label that angle as theta prime. So theta prime is going to be equal to the arctangent of 4/7, which if you put it in your calculator, that's roughly 29.7 degrees. But since we want the third quadrant angle, because that's where our vector is, we're going to need to add 180 degrees to our theta prime. So our direction angle would be theta prime plus 180 degrees, which is 29.7 degrees plus 180 degrees, which gives us 209.7 degrees. And there you have it. So here we have an application of direction angles and finding the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle of 15 degrees below the horizontal. Here, looking at the graph, they give you that the actual direction angle is 195. If we look at the airplane or the vector, the velocity vector being on the third quadrant, we are remember the direction angle always comes off of it's always formed with the positive x-axis and the vector. So labeling everything that we have here is vector v for velocity. Its magnitude is 100 because the velocity is 100 miles per hour, and the direction angle is 195. So for problems like this, when the angle is provided or is easy to calculate, we can use our representation that we had before. Vector v is equal to its magnitude times cosine of theta I plus magnitude of v sine of theta j. Remember, I and j are vectors, are the standard unit vectors. So we plug in everything in. We have that vector is equal to 100 cosine of 195 degrees I plus 100 times sine of 195 degrees j. And make sure that your calculator is in degree mode if you're going to plug this in. Okay, putting this in the calculator, we have a negative 96.59 I minus 25.88 j. And we can also write it in component form, which is actually what they ask, and have it in our triangular brackets as well. And here we have it. And you can also verify that the magnitude of that vector is actually 100, which is the speed here.